Be on. So I will make the introduction. We're very happy to welcome Dr. Rachel Ward today. She is an associate professor in the math department at the University of Texas at Austin. And she has done all sorts of work, if I remember correctly, on inverse problems and things like that. Today, she's going to talk to us about weighted optimization and how one could get good generalization properties by studying smoother interpolating, let's say, predictors. So Rachel, welcome, and the floor is yours.
Thank you very much for the invitation. Here I am giving a talk out of my garage. And please feel free to interrupt at any time if you have questions. This shouldn't be too long of a talk. This is actually the same talk I gave at an ICML workshop a few weeks ago. What I'm going to talk about is really simple. It's just sort of looking at this, I guess, newly emerging interest in the field of machine learning in the benefit of over-parameterization in sort of neural network optimization. And hopefully I'll have you can see a different perspective here coming from my background in compressive sensing and harmonic analysis, maybe on the benefit of over-parameterization in neural network optimization. So that's my talk. This project was led by my PhD student, Gail Shi at UT Austin, and Edward Shou and Holger Rauhut at University of Aachen. And wrong arrow. So first I'll give some background introduction to the motivation problem that we're considering. And then I'll give some theorems concerning generalization risk bounds for interpolating with Fourier features and the importance of normalizing the features in the correct way in terms of the resulting generalization bounds you get in the over-parameterized setting. And then I will talk about how this is connected to the situation in nonlinear deep learning optimization problems. So the motivation is probably this picture that you all have seen now many times. This is a picture of this so-called double descent or extended bias variance trade-off curve that Belkin and co-authors sort of promoted. This is motivated by a few curiosities of modern deep learning. I would say the first curiosity, which we're not addressing in this talk, it's just something that you should accept as something I'm going to just take as something that's true without proof, is that neural network optimization problems in the supervised setting, in the over-parameterized setting, are highly non-convex, but gradient descent, stochastic gradient descent, can still find global minimizers where the training error can go all the way to 0. And so we don't really know why this happens, but we're just going to take this as true. The second curiosity, we're starting to understand a little bit more, is that state-of-the-art neural networks really achieve their best performance in terms of lower generalization error, or better generalization performance in the over-parameterized regime, where you just put a ton of parameters in the neural network model and just run gradient descent or stochastic gradient descent until the training error is 0. So from a math perspective, we just say the interpolation regime. So we're just finding a function within our certain neural network parameterized class of functions that fits the training data exactly, and then observing that when we do this, the function is a good approximation for samples we haven't seen. So that's what generalization is. And so this is a bit different from the classical statistics approach, which just sort of looks at the bias variance trade-off curve in the under-parameterized regime, where there's a careful balance in choosing the number of parameters to be smaller than the number of training data n. But this is saying that don't worry about that careful balance, just take the number of parameters p to be much larger than n, and you'll get even better, often, performance than in the underparameterized regime. So the situations where you can see good generalization performance in the overparameterized regime, that's a very special situation, and is very much connected to the particular algorithm you use. Because in the overparameterized regime, there are many possible functions that interpolate your training data exactly, and it's the particular algorithm and it's biased towards one of those particular interpolating functions that will have good generalization error. So in deep learning, people optimize with gradient descent, very simple algorithm. So in order to understand this double descent curve, or situations where we can benefit from overparameterization, we need to understand which interpolating function gradient descent goes towards in this overparameterized regime. And we don't know the answer to this in the setting of deep learning exactly, but a flurry of papers recently have been trying to understand the implicit bias of gradient descent on simpler optimization problems as models for the sort of nonlinear neural network optimization problems. And it's still an interesting and rich problem to try to understand these risk bounds, even for linear interpolation problems optimized with gradient descent. So it seems like perhaps this is a much simpler problem, but it's still quite interesting to ask, when do we see a sort of double descent curve like this when we're just doing a linear interpolation problem that we're optimizing with gradient descent? And so that's what I'm going to talk about. So what is linear interpolation or regression? The setting is we have n labeled or n training data, xk, yk, where xk comes from a closed bounded domain. Yk here is real number, so we're not looking at classification here. So yk is equal to f of xk plus maybe some small noise, and f is say the function that is unknown. We don't know f. And we have some prior knowledge that tells us that we think we have a good set of features, phi 1 through phi p, or a basis of functions, that we believe this underlying function f is in the span of these features. And so the linear interpolation problem is when the number of features p is greater than the number n of training points. And we just find one, we find a function in the span of these p feature functions that fits the data exactly. That's this over here. This is the interpolation regime. The regression regime is just when we do a linear least squares problem and we look for the function in the span of these p features, minimal L2 norm error to the samples. The interpolation problem, it's a function of which algorithm we use to find an interpolation, which tells us which of the infinitely many interpolating functions we converge to in the span. And so in this linear problem, it really is just a linear algebra thing here. We have phi theta minus y L2 norm squared if we're minimizing the empirical risk. Phi is in the overparameterized regime, a short fat matrix. P is greater than n, so phi is a short fat matrix. Its columns represent the p different features evaluated at the sample points, and the rows are indexed by our training samples. And so that's the matrix phi, and there are infinitely many parametric solutions theta such that phi theta is equal to y exactly. And some of those theta will correspond to interpolating functions that you don't want to use for interpolation. They just look really bad. They could be very, very wiggly. and they're not going to have good generalization. Other ones of them are going to be better. But everything can be studied just in terms of this linear algebra problem. Phi theta equals y.
Quick question,
yes.
if I may. So is your starting hypothesis that non-smooth interpolators will generalize badly?
Yes. So I sort of took a long time to get to this, but what would be considered a better interpolator? A non-smooth interpolator will generalize badly if the underlying function f is smooth itself. So, and so we have to make some assumptions if we want to talk about generalization bounds from a finite number of samples. We have to make some assumptions, otherwise, you know, you have finite number of data and infinitely many possible functions. So I think a pretty reasonable assumption in the setting is that the underlying function f is smooth. So if we assume that the underlying function f is smooth, then you can imagine that the smoother the interpolation we go to, the better generalization we'll have.
Right. That's kind of my understanding too. I've seen some work by Su and Belkin, for example, where they study either kernels or weighted, let's say weighted KNN, if I remember correctly. And some of the visualizations they use in their paper or in their talks have quite non-smooth interpolators. And I've been trying to understand that element of their
as a
work.
good thing? In the sense that the non-smooth interpolator is something good?
I don't think they're making that point explicitly, and it might not be even a point that they're making at all. It's just the visual that was similar, and I don't fully understand what's happening there. So I wonder if you...
I haven't seen the KNN work, I think.
Okay.
But I will say that I think you guys are all familiar with this double descent curve. When Misha Belkin was giving talks on this, he said that this benefit of overparameterization is connected to the ability to get smoother and smoother interpolations as the overparameterization P gets larger. Or that was sort of an intuition as you just increase the number of parameters, enlarge your model class. If your algorithm has the right implicit bias, it can find sort of smoother and smoother interpolations. And that was go ahead.
I think maybe then it's an artifact of the visualization. It's a one-dimensional function. So when we interpolate, it needs to have those spikes. But this in high dimensions, the landscape changes completely.
Yes, and another funny thing here is you see this curve here with these little spikes, this P greater than N curve, and you could say this doesn't look smooth at all, but I might argue that this could still be somewhat like a smoothest function that goes through these training points exactly in the model class, if the model class is like polynomials.
Right, right.
Okay. So there might not be a contradiction there. It might all be consistent. I'm just talking as I go. I just realized that. But in all of this, there's been a lot of work on understanding generalization error for sort of random linear models and so on. But I wanted to understand, we wanted to understand sort of a bit more concretely, intuitively, the connection between the type of features in the model, the normalization of these features, and the connection between this and smoothness of the resulting interpolation and generalization error, just in the linear setting. And so that's what I'm going to, I think you guys probably know, I've seen that gradient descent as an algorithm just applied to the least squares loss in the overparameterized regime has an implicit bias towards the parametric solution theta of minimal L2 norm. in the sense that this gradient descent algorithm, if we initialize at theta 0 equal to 0, if we initialize gradient descent at 0, and then just run gradient descent with a step size that's small enough that gradient descent converges, it's a property of the algorithm that the thetas at each iteration will stay in the range space of the feature matrix phi, and thus will converge to a parametric solution theta satisfying phi theta equals y, which is in the range space of the feature matrix phi. And the only solution theta to phi theta equals y that's in the range space of the matrix. By range space, I mean row space, sorry. The row span of the matrix phi is the solution of minimal L2 norm. So just
Nicolas had a point to add.
Yes, please. Nicolas knows more about this than I do.
It was meant to be this too discreet. No, it actually is. What we hadn't realized is that it's also true if you use any preconditioner that leaves the span of the data unchanged. And so the Newton method has the exact same implicit bias. But any diagonal preconditioner will lose that bias because it leaves the span.
Any diagonal preconditioner will leave the bias.
We'll leave the span of the data, and so the implicit bias will not be the same. But like if you use full matrix Adagrad, you get the exact same implicit bias because full matrix Adagrad is the bunch of outer products of XX transpose. And so you get exactly the same thing. So you have quite a bit of freedom to keep that bias.
Yes,
Yeah.
you do.
That's all.
Yes. And so I guess I just want to emphasize the point that people often talk about which features, like for different classes of features, what the corresponding generalization error would be, and so on. But what I want to emphasize in this talk is that if we just fix a set of features, just the way we normalize these features will have a very great effect on what the interpretation of the minimal L2 norm parametric solution in terms of smoothness of the resulting interpolator. So everything's very sensitive. The bias is sensitive. I think this is what Nicola was saying, just to how we normalize a set of features, which is equivalent to saying what fixed diagonal preconditioner we might apply to gradient descent, or the way in which we might normalize in stochastic gradient descent the step size depending on which feature we're in. And the normalization is very important. And so that's what I want to focus on here. This is sort of an aside slide, just to say that understanding the bias, implicit or explicit bias of different algorithms in the over-parametrized setting is not something new to deep learning. I mean, this is what compressive sensing, the area of compressive sensing a decade ago was all about, just where the explicit bias was towards a minimal L1 norm parametric solution instead of minimal L2 norm parametric solution, which I'll say minimal L2 norm or weighted L2 norm solutions are gradient descent. Minimal L1 norm solutions are what compressive sensing was all about. And like I, with a co-author and other people, were looking at minimal L1 norm parametric solutions for function interpolation problems, because smoothness of function of a function is characterized by its rate of decay of its Fourier series coefficients. And so especially for higher dimensional functions, they'll have a big decay in their Fourier series coefficients, as well as sparsity in their Fourier series coefficients, sparsity depending on which directions the function are important, because high dimensional functions are often really only dependent on a few important directions. And so in any case, we looked a long time ago at the way different explicit bias is connected to smoothness of interpolating functions through data. And we found then that looking at minimal L2 norm, so looking at functions where we look at the minimal L2 norm of their Fourier series coefficients, Fourier series are the features now, the way we weighted the Fourier series features had a huge impact on how the interpolating function was. Without any weights on the Fourier series features, we saw lots of overfitting, not very good generalization. But if we divided the Fourier series features by weights, where the weight is agreeing with the norm of the derivative of the Fourier series, or the weight is getting larger at higher frequency features, then we saw smoother and better fitting functions. And so that's really the point that I wanted to get back to here. If we're going to take a look at Fourier series features as a model, because Fourier features are, I think, becoming more and more important even in deeper learning optimization. They're pretty important. And look at how weighting Fourier series features affects the generalization error in these optimization with minimal L2 norm Fourier series solution. And then we'll explain a little bit more concretely how this is connected to deep learning, where the features aren't necessarily Fourier features, but there's still a notion of frequency, and higher frequency features we want to normalize in a certain way to downplay, to de-emphasize higher frequency features to get better performance. So for the Fourier series interpolation model, this now is very concrete. I just observed n training samples at equispaced points, so xk equispaced points on my domain, which we can just assume is -1 to 1. It's just a univariate problem, so domain there. And our yk that we observe are evaluations of an unknown function evaluated at xk. So the function is unknown, but it has a Fourier series with Fourier series coefficients theta tilde theta. And if we assume that our f is a somewhat smooth function, that means that these tilde theta will have some decay. So the lower frequency ones will be higher. And then we look at the problem of interpolating with weighted Fourier series features. So we just fit by minimal L2 norm parametric solution in the span of the first P Fourier series, where we weight the Fourier series features by weights, where we'll consider either the weights to be all equal to 1, which might be the first choice, and then we'll look at weights which are increasing on the higher frequency Fourier series. And when we talk about performance, what we mean is the risk, which by Parseval's identity for Fourier series, it means that actually the risk in the parameter space, meaning the L2 norm difference between the true Fourier series and the one returned by the recovered one, is equal exactly to the L2 norm difference between our underlying function and the interpolating function. So usually there's like a difference between a result in parameter space versus function space, but here it's the same because the Fourier series is an orthonormal basis. And so just the first maybe naive thing to do is to just look at the Fourier series coefficients of minimal L2 norm. When we look at the span of the first P Fourier features and look at the interpolating function, first when P is equal to n, so this is at exactly interpolation. Just in this example, we get interpolating function being the orange one. And then as we increase the number of parameters, we increase the degree of our Fourier series model that we're fitting to, the interpolating function gets much worse. So we're getting no benefit from overparameterization if we just do interpolation with Fourier series without thinking about normalizing the features.
A quick question. if I may.
Yep.
It's about your weighted Fourier series features model, right? So you have those phi's weighted by omega. So phi j omega is one feature, right?
Yes.
And they're orthogonal to each other by construction. So you have your basis, and then are you fitting a linear model using those features?
Yes.
So then I'm a little bit confused about how this weight omega you're using makes any difference, unless you're bounding your coefficients, right? Are you limiting the magnitude of your coefficients in that linear model?
No. Yeah, this is a really, so it doesn't make a difference in the underparameterized regime. In the underparameterized regime, the weights make zero difference. And I should have emphasized that more. There's a unique, least squares, optimal least squares solution in the span of the features. But in the overparameterized regime, when there are infinitely many possible interpolations, if your algorithm is biased towards the parametric solution of minimal L2 norm, it depends entirely on these weights, what the minimal L2 norm means.
Okay. I think I get it.
And actually, it's probably simpler to say that by change of variables, you can see that the normalization is equivalent to if we do look for a minimal L2 norm interpolator or minimal weighted L2 norm interpolation. And so weighted L2 norm interpolation with the unnormalized features, I mean, where the weights will promote lower frequency functions rather than the high frequency functions. Yeah, this is not intuitive, and so I'll try to figure out a better way of saying it. But here, without putting weights on our Fourier series features, gradient descent or the minimal L2 norm parameter solution is actually just the interpolating function within the span of the features that itself has minimal L2 norm or minimal L2 norm of the integral. So in other words, the function's going to want to come back to zero between fitting every interpolation point. It's just going to want to oscillate back to the origin. So this is an entirely stupid thing to do, and you're not going to see any benefit from overparameterization. Now, if instead we look at the Fourier series features and we divide e to the I jx by essentially the norm of its derivative, j, or the Lipschitz constant, basically the Lipschitz constant of that feature. And then we look at the minimal L2 norm solution with respect to this normalization of the dictionary. We see that as the features increases, we can get smoother and smoother interpolations of our data. So this is when p equals n, and this is when p, if we take a number of Fourier series functions much greater than the number of samples we have, it's still, because we had noisy training data, it still doesn't look great, but it's an exact interpolation, and it's smoother and smoother as p gets bigger, in contrast to not weighting the features.
Rachel?
And, yeah.
Can you just repeat the argument for why in the unweighted case it had to go through zero between every point?
Sure. It doesn't have to go through zero, but in the unweighted case, you see that asking for a minimal L2 norm parameter solution, theta, is equivalent by Parseval's identity to asking for a function f of theta hat, asking for a function which itself has minimal capital L2 norm. So it's trying to find, it's asking to find a function in the span of, with a truncated Fourier series representation with smallest integral that passes through the data points. And so if you think about trying to minimize the integral of the interpolating function such that it passes through the data points, to minimize the integral, it's going to want to come back down to the origin to minimize the area under the curve. Is that?
Well, I'm just confused because it's the difference between the true function and the other function. So I don't see why, if you look at the next slide, the one which is smoother with the weighted thing should not have an even lower L2 function, L2 norm.
I understand what you're saying. Do you see my mouse right here?
Yes.
Okay, so pretend that this is 0. Parseval's identity still says that the L2 norm of just theta hat is equal to the L2 norm of f of theta hat, the functional L2 norm. So if we're looking for a solution of minimal theta L2 norm, that means the bias is towards an interpolating function, which itself has minimal L2 norm by Parseval's identity.
Okay.
So not only is this risk-bound inequality, but also the L2 norm for any, just for the theta itself. And maybe that's clear here. So Fourier analysis tells us why we want to weight the Fourier series features by the magnitude of their derivatives. This is because with the Fourier series weighted by 1 over their frequency, by 1 over j, the minimal L2 norm parametric solution theta, which goes through the data, is equivalent to, in function space, the minimal interpolating function of whose derivative has minimal L2 norm, plus the function itself has L2 norm. This is called a Sobolev norm in Fourier analysis. A Sobolev norm is a smoothness norm, and it's a classical sort of norm you want to minimize for interpolation in interpolation theory. So you want to minimize the integral of the derivative of f, not just the integral of f, which will have it be very oscillatory. You want to actually find a smooth function through the data. And if I were to take these weights to be not 1 over j, but 1 over j squared, then that would be equivalent to having a functional bias, which also penalizes the second derivative of the interpolating function. And so...
I'm sorry, Rachel?
Yeah?
I would have thought that when you use omega j equals j plus 1, you're only minimizing the square norm of the derivative, not the sum of the two square norms.
Right. So you get the sum because we're including the 0 frequency in the basis. And the 0 frequency actually corresponds to the norm of the function squared. For a function, the integral of a function squared is equal to the value of the function's Fourier transform at 0 squared. This is duality between, and so that's and you really need that there to make what you're minimizing a norm rather than a semi-norm. Without having the function there also, if you're just minimizing the derivative of the function, that's not a norm. And
okay, but so when you use omega j equals j plus 1 squared, do you minimize really the sum of the value first and second derivative, or just value and second derivative?
The value and then the second derivative.
Okay, yeah, okay,
yeah.
Cool. Thanks.
Yeah, and I realize that this isn't as clear as it could be, and please feel free to go to our paper of the same name as this talk to see more details and references there. But so we have this. So this is with understanding the concept of Sobolev norm and duality between multiplication and differentiation in time and frequency. it's understood why you want to at least normalize the Fourier features by their frequency, perhaps steeper weights that decay even more. But still, the Fourier analysis doesn't give any sort of generalization bounds. So we still want to know what can we say about generalization error precisely of such sort of minimal smoothness and turbulence. And of course, we're only going to be able to see a benefit of overparametrization if we're looking for a smooth interpolation if our underlying model is itself smooth. So if our yk equals f of xk and our underlying f has like 3 derivatives, so it's very smooth, then we could get very good generalization error in the overparametrized regime by minimizing a Sobolev norm, which penalizes the 3rd derivative. If our underlying function is only smooth in that it has, say, a 1st derivative of good norm, then we would only use weights in our interpolation that assume that penalize the 1st derivative, the norm of the 1st derivative. So in order to get some sort of risk bounds, what we had to do was first assume a random model for a smooth function that we assume our data comes from. So what's a model of a random smooth function? Something that made sense to us was to consider a function with which is a trigonometric polynomial of degree d. So it has a first d, an expansion in the first t Fourier series functions. And its Fourier series coefficients, theta, is a random vector, which non-isotropic covariance. So it has some decay. So it's a random vector, which is mean 0, and its covariance matrix is a diagonal matrix, which has a decay like 1 over j to the 2r, where r is a number between 0 and whatever. So bigger r means our smoothness, we're assuming a sort of smoother underlying function. It's a stricter and stricter assumption, the bigger r is. If r is equal to 0, then this model reduces to an isotropic covariance model, which, like Belkin and all, analyzed as a univariate version of random Fourier features in their one of their first papers on this. So the r equals 0 case here sort of reduces to an isotropic model that people have been studying lately. But r greater than 0 is sort of a model for smoother and smoother functions. And then we observe equispaced training data. We fit the data with weighted Fourier features, as I've been talking about, where the weights in the Fourier features are to the power r, taken to match the model. So the smoother, if we assume a smoother underlying function, we take the same factor r here when we normalize our features. And we're also going to try to derive risk bounds in the under-parametrized regime just to match, to see if we do better in the over-parametrized regime than the under. And remember, in the under-parametrized regime, the normalization of the features doesn't matter. There's just a unique least squares fitting function in the span of the features. So the risk expressions we get are exact, and they're yucky. So I'll just present sort of the bound we get. What we see are we get these risk curves. The orange are using weighted Fourier features where the weights match the smoothness of our underlying function, and the blue curve is not doing weights, just using Fourier series without normalization. And so we see that in the 3 plots, our underlying function is getting smoother and smoother. Here r is 0, here r is 0.3, here r is 0.5, here r is 1. So the smoother our underlying function is, the more benefit we see in the over-parametrized regime by normalizing our features to match that smoothness. And so we see a sort of double descent here when we do the weighted Fourier feature interpolation, whereas without weights, there's no double descent. You don't gain from overparameterization. And then by the time your underlying function is nicely smooth and you have a pretty strong smoothness prior, the overparameterization, you don't have double descent anymore. You just get better and better generalization as you increase the parameters of the model, and there's not even any close match with the unweighted interpolation. And the precise risk bounds we get are of the form, as long as R is greater than 1/2, then the expected risk, we have to take an expectation with respect to the random Fourier series random vector in our model, is bounded by like n, the number of training data, to the power -2r plus 1, plus a second term n to the -2r times p to the -2r plus 1, so that as p goes to infinity, that second term goes to 0. And that's the benefit of overparameterization. The risk goes down as p goes to infinity. Also, the risk goes down when your data is coming from a smoother function, R is bigger, and you interpolate with your normalized features to match. And if you go into approximation theory literature on Fourier analysis, there are results that say that this error, this risk, is like order optimal in terms of n and R, I suppose. So these are just some overview of some of the theoretical results we have for this model. So we can understand the behavior of the benefit of overparameterization pretty completely in this simple Fourier series model with correct weighting.
A question?
Yes.
Okay, so if I understand correctly, this parameter R controls how aggressive your weighting is?
Yes.
Right? So higher values mean more aggressive weighting?
Yes.
Yeah. Okay, and my understanding from our discussion earlier was that I should, this should have an effect, this changing R should have an effect in the overparameterized regime, because in some sense it changes what kind of norm you use when you're looking for this minimum norm kind of solution.
Yes.
But I see that it also has an effect in the underparameterized regime.
Yes, it has an effect in the underparameterized regime.
And is it for the same reason? Is it because I expected that in the underparameterized regime, we would have an overdetermined system. So you would always have one solution, right?
There's always one solution so the one solution, yeah, sorry for this confusion. There's one solution, but still R is used in sort of the ground truth data. R is used is the degree of non-isotropicity. It's not a word. Of the ground truth data that the samples come from. So when R is bigger, you are going to get lower risk also in the underparameterized regime, because more of the energy of your underlying function is in its first so many features.
I see. So your ground truth also changes.
The ground truth changes, yes. The distinction is that in the overparameterized regime, whether or not your normalization of the Fourier features takes that ground truth into account or not, that's a parameter of the optimization method. If it does take it into account, you get a benefit of overparameterization with the orange curve. If it doesn't, if you don't weight the features according, you get this. Because you get those functions that just oscillate more and more through the origin. They're not doing anything.
Yes, so just to clarify here, the R was used in two places. One was for the ground truth, the other one was for the reweighting.
Yes,
And
so yes.
The reweighting doesn't do anything in the underparameterized, that's why blue is on top of orange.
Yes,
but
exactly.
The ground truth changes, that's why from left to right there are some differences.
Yes. And in our paper, we have two parameters. We have an R and a Q, where R is the ground truth and Q are the weights used in the optimization. And we have more plots for various R and Q, but I just made them sort of, you can make those two free parameters, one the model and one the optimization.
Okay.
These are some citations to really interesting work on sort of understanding the ridgeless regression situation. So from the statistics point of view and using really nice results from statistical physics to understand asymptotic bounds on the risk for certain linear models and nonlinear models where the parameters n and p go to infinity. And so they get nice risk bounds in that limit when n and p go to infinity together. And I don't see exactly how to use the statistical physics point of view to understand this overparameterization benefit, how that connects to smoothness, because smoothness is very important here. But that's an interesting question for people that I would like to see. Our point of view allows us to get bounds on the risk in the non-asymptotic regime when n is anything and p is anything. But the limit of our analysis is that d, the dimension of the functions, is 1, which, of course, in deep learning problems, the interesting case is high dimensional function interpolation. D is big. So, and then this question mark here is just the one of the first analysis of Belkin et al. Paper on Fourier series features with R equals 0, getting some asymptotic risk bounds, but they didn't show the benefit of overparameterization because there isn't any if R is equal to 0. So I guess I want to just quickly try to convince you that this little model we had actually is connected to the setting in neural network optimization. If I were to try to do a higher dimensional version of what I was talking about before, where we don't look at univariate function interpolation, but multi-dimensional function interpolation, and we look at tensor products of univariate Fourier series to consider a multi-dimensional Fourier series, then the weighting is not going to have any effect anymore, because in higher dimensions, we can't consider multi-dimensional Fourier series. The number of basis functions is too big. So we would do random Fourier features instead. Of the Swarhemian rect, random Fourier features can be seen as a way to extend univariate Fourier series to high dimensional function interpolation. So the frequencies in random Fourier features are not 1, 2, 3, 4, 5. They're random Gaussian variables. The frequencies are random themselves. But because of concentration of measure, a lot of these random Fourier feature frequencies, they're going to concentrate around the same norm. That is the concentration of measure. So whether we weight them by the norms of their frequencies or not is not going to change the problem that much, because all of these norms are about the same. However, if we go to higher dimensional problems where the frequencies themselves in the random features are parameters that we can optimize, then we can consider certain weighted optimization to try to move the frequencies in a certain way to promote smoother solutions. And I'm just going to give an example of what I'm talking about, just a one hidden layer neural network. The features in a one hidden layer neural network, for example, could just be these nonlinear features. Sigma of inner product between Wj and X, where sigma is a ReLU nonlinearity activation function, and Wj is a frequency in our setting, but it's a frequency that's a free parameter. So we initialize it as a random frequency, but then we can optimize it. We can actually do feature, so we can change the features. So the features are no longer orthonormal, like in the Fourier situation before, but still we can bound the gradient of such features by the norm of their frequencies. So that doesn't change. So it still makes sense to consider weighting our nonlinear features by dividing the features by the norms of their frequencies, just as I was talking about before. Except now, these frequencies are themselves parameters. So by normalizing by the frequencies, we're normalizing by something that we can optimize. And so what we're doing is we're reparametrizing the extension of what I've been talking about to, say, nonlinear feature interpolation corresponds to reparametrizing the loss function in a way that looks like this. Our theta are parameters and our wj's are vectors of parameters. And in fact, what comes out is a normalization that's very similar to weight normalization. Sorry about these question marks. Weight normalization, which is somewhat connected to batch normalization, where you normalize your features to make them scale invariant. And the motivation for these other normalizations was not to improve generalization by fitting with smoother interpolations, but rather to accelerate training. And batch normalization was motivated by a certain thing, which seems to not be the reason it's so effective. So I don't think batch normalization is really understood why these normalization methods are extremely important in practice to get better generalization error. That's the end point, is that what I showed you was that by normalizing features a certain way in these linear problems, we can provably show that the generalization error in the overparameterized regime goes down. In practice, similar normalizations are applied to nonlinear neural network interpolation, and generalization error is observed to go down. So our hypothesis is that this is connected to promoting smoother interpolations in some way through these reparameterizations. And this is just some experiments showing that the weighted optimization reparameterization I just showed you indeed leads to higher test accuracy in standard models. Here we have MNIST, but we also did, what's it called? Not ImageNet, but the CFAR. Okay. So of course, the second part of the talk was not rigorous, and so there's more to say there, but somehow we see that neural networks and for supervised learning problems give best performance in the overparameterized regime. This is somehow very connected, I think, to the way that they're normalized, these normalization methods, batch normalization in particular, and that's also connected to encouraging somehow smoother interpolations, which have better generalization error, and there's more to be understood there. But we gave a new connection, I think, to Fourier analysis, between Fourier analysis and these optimization methods for deep learning. And yeah, I still don't know anything about neural networks, unfortunately. And there's a lot more to be done. And of course, the implicit bias of gradient descent in neural networks is not just about smoothness. That itself is just a simplification. The implicit bias is really, there's sparsity, there's smoothness, there's what is the implicit bias of gradient descent on deep neural network architectures. I don't know, but that's all I have. Thanks.
Thank you. Thank you, Rachel.
Thanks for listening.